So this is about Ptolemy belief systems and other dark matters. Now, we're all here or watching online because we have an interest in the exploration and an explanation of the cosmos. Now, when we think about the investigation of the cosmos, we often focus on the capabilities and the limitations of the instruments and the observational tools that we use. We lose track of the limitations that are imposed on us by possibly the greatest instrument and most critical instrument involved in this exploratory process. And that is, of course, the human mind itself. Now, unlike the instruments of our invention, the human mind really hasn't changed very much, if at all, since we took our first steps on this great journey. I often talk about how we have not really changed very much from our previous selves. So many thousands of years ago, when we huddled together trying to figure out what populated the darkness beyond the campfire. And so we lose track of how the greatest challenge ahead of us is not really the precision of our mechanical or electronic instruments. It's the cumulative psychological and sociological and biological and evolutionary hindrances in our own mind. Now, I plan to talk about this for the next little while, but first I thought it would be instructive to open with a story. And this is the story of the clever king and the sage. Now, once upon a time, there was a clever king. In fact, he was so clever that it was widely held that he was the most clever person in all the land. More clever than anyone who'd ever been before, and probably more clever than anybody would ever be. And one day, the clever king decided that he would devote all of his cleverness and all of his kingly resources to enriching the lives of his subjects by discovering secrets of the cosmos, the sun, the stars, the earth, and even life itself. And so he collected all of the clever people in his land to help him in this great work. And for many years, the king toiled with his hundreds of clever people in constructing the most amazing, sophisticated, complicated mechanism ever built. They poured all of their collective knowledge into it, all of their cleverness. Nothing was missed, no mistakes were made, and it was wrong. The magnificent machine, so complex, did not explain the cosmos, the sun, the earth, the stars, and life itself. It always gave something different than what the king could see. Something was wrong. So he was so confident, he knew, he was certain, in fact, that something little was missing. They had poured so much of their knowledge, so much of their cleverness into this machine. It had to be something incremental. So in frustration, he looked for other clever people who could come and help him find these missing pieces. And finally, he heard of a sage, an old wise man who had wandered through all of the kingdoms and was said to be as wise as time itself. So he summoned the sage to come before him and look upon this great work. And so the king explained, piece by piece, this incredibly complicated, beautiful machine, showing him how all of the cleverness, all of the knowledge had gone into it. And the old wise man nodded and smiled, and he blinked in wonder. And he said, "My king, I can tell that indeed you are the most clever person in the land, more clever than anyone who's come before, and probably more clever than anybody will ever be. But," he said, "I can immediately see what it is, where the missing pieces are that will complete your great work." Well, the king was overjoyed. He was amazed. This is fantastic. He knew he had done the right thing, bringing in that sage, right? So he said, "This is great. Can you please tell me what the missing pieces are so that I complete this great work?" And the wise man said, "The pieces that are missing are all the things that you don't know that you don't know." Well, the king was dumbfounded. He sputtered in frustration. He said, well, how am I going to complete this great mechanism if I don't even know what I don't know? And the old sage nodded and smiled, because now he knew the king was asking the right questions. And he said, my king, when I first met you, I knew you were the most clever person in all the land, but now you're just a little bit wiser. Well, I can't say the king took that very well, but the moral of the story is that the clever man has complete confidence in the cleverness of his inventions, and that complete knowledge is just a few pieces away, just a few more pieces to complete the picture. The wise man accepts and acknowledges that we can never really know what we don't know, which means we can never be certain about anything we think we know, and that the pursuit of absolute certainty is probably a foolish goal anyway. Now, there are a couple things I like about this story. One of them is this metaphor of this machine for conceptual frameworks. After all, a system of differential equations is really just a mathematical machine. You crank away at it, sort of algorithmically, and answers and simulations come out the other side. And if it agrees relatively well with some subset of what we observe, we get quite a bit of certainty that in its general use. And this ingrains some belief that it can be used in all conditions. Well, modeling mimics understanding. Now, over the course of our history, we've constructed various complicated conceptual frameworks to try to understand the workings of the cosmos. Now, one of these very complicated conceptual frameworks can actually trace its lineage back to ancient Greece and Aristotle, but it was actually perfected by Claudius Ptolemy. And this is, of course, the geocentric model of the universe. This notion that the sun and the planets revolved around the earth. Now, Claudius Ptolemy was an observational astronomer and a mathematician. We actually don't know very much about his life, except that he lived and worked in Alexandria at about 150 AD. Now, however, most of his work actually survives. And foremost amongst this is the Almagest, which is a treatise in 13 volumes that describe the motion of the sun and the planets. And indeed, the universe was conceived as a great mechanism. Nested planetary spheres comprised of a perfect crystalline substance called quintessence, or ether, and the planets riding on the crystalline spheres. Now, quintessence has a natural, perfect circular motion, and also it can never be experienced here on Earth, where we could only experience the normal elements of earth, air, fire, and water. And now we have this notion arising of some disconnection between the physical nature of the heavens and what can be experienced here. We actually see this recurring in modern cosmology. We'll talk more about that later. Now, one of the things that I like about this model, one of the things I find interesting, is this creation of new physical entities and mechanisms to fill in our gaps in understanding. What we don't know, we populate with new physical entities. And as our imaginings are modified and adapted to fit with what we observe, then these imaginings are transmuted into an illusion of understanding. Now, probably Ptolemy's great innovation was the use of the equant and the use of the epicycle and deferent. Now, through multiple spheres per planet, and it's a sophisticated use of epicycles and deferents, he was able to construct a very complicated system to predict the motion of the sun and the planets. And here we see in this animation that through this use of epicycles and deferents, he could model that back and forth wandering of the planets. And actually, the Ptolemaic model was relatively satisfactory. And from a mathematical perspective, was probably one of the most outstanding achievements of the human mind. In fact, it's very difficult to identify another scientific system of thought that was so successful in predicting for so long. For over 1,400 years, it dominated as our view of the cosmos, at least until the advent of Copernicus. Now, Nicholas Copernicus was originally educated in art and mathematics, but when he became canon of the Frombork Cathedral, he traveled to Italy ostensibly to study religious law. But what he really did was he dived headfirst into astronomy, and he made full use of the books that were available at the time due to the recent advent of the printing press. Now, we all know that Copernicus made that great leap in placing the sun at the center of the cosmos, and he was largely motivated by a sense of simplicity and elegance, the theme of this conference. But he also believed very strongly in Plato's notion of perfect circular motion. He abhorred Ptolemy's equant. But because he was limited to circular motion, he needed to use the epicycle and the deferent to make his model match what was observed. Now, to a certain extent, it was more simple and elegant than the Ptolemaic model, but it's arguable whether it was really that much simpler. And in fact, in real practice, it didn't really provide that much better prediction, if at all, than the Ptolemaic model. There's also something on the heretical side as well. And Copernicus took great pains during his life not to actually broadcast these notions, and was only really published very shortly before his death in 1543. And he was right, because in the oncoming years, the church condemned the work, and the book was added to the list of banned books in 1616. And so the geocentric model persisted, even in the face of some fairly convincing contradictory evidence that was coming forth from Galileo. Now, Galileo was working with the telescope, which was just invented in 1609, making some really critical observations like moons around Jupiter and craters on the moon and sunspots. But his most critical observation of all was probably that of the phases of Venus. The phases of Venus, these observations were completely inconsistent with the geocentric notion of the universe. If the geocentric model was a scientific hypothesis, it would have been disproven out of hand. And it's a wonderful example of how humans can ignore evidence that contradicts their strongly held belief systems. Well, it's fair to say that life became uncomfortable for Galileo. Inquisitions tend to do that. So he eventually recanted, was exiled, and the geocentric model persisted. Now, in the meantime, Kepler was working away and did away with this notion of circular motion and developed a new empirical set of planetary laws of motion based on the ellipse. And he sort of set the stage for a true revolution in human thought. But it was the groundbreaking work, actually, of Isaac Newton that really did away with geocentrism as our dominant view of the cosmos. Now, Newton began his groundbreaking and amazingly broad range of work when the scientific revolution of the 17th century was in full swing. His new notions of gravity provided an exciting new explanatory framework for the motion of the planets. He established a unified earthly and heavenly system of mechanics. He was able to independently mathematically derive from first principles, Kepler's empirical laws of planetary motion. Now, the power of Newton's system lay in its universality. It tied together the physical phenomena, both earthly and heavenly, into one system. There was no longer this separation between the physical nature of the heavens and what was on Earth. And it's interesting that this separation, this connection between what happens in the heavens and what happens on Earth has only been recently severed again. But more on that later. Now, the way to Newton's power to this universality was through mathematics. And the title of his book, The Mathematical Principles of Natural Philosophy, sort of speaks for itself. It embodied and inspired this notion that the universe could be reduced and accurately modeled through mathematical formulation. But Newton himself admitted that, and if I can paraphrase, he had found the laws but not the cause. He, even though had not really described the underlying physical principles, the cause behind gravity, he had established that this new system of the world was uniquely grounded in gravitational laws. And it's been immensely successful. I mean, it's Newtonian mechanics that launched rockets and satellites into orbit and put men on the moon. And our lack of understanding of what underlies the gravitational laws has in no way kept us from taking full advantage of its mathematical description. So again, we've been lulled into a sense of understanding. Now, with the advent of field theory, inspired by the work of Michael Faraday, we did away with this mechanical notion of the universe and replaced it with more abstract notions of field of influence. Ultimately, Clerk Maxwell mathematically codified Faraday's empirically derived laws of electromagnetism. But Einstein applied field theory to a fairly major refurbishment of the gravitational laws in the general theory of relativity. And it's with the general theory of relativity that we turned our faces to the natural world. We embraced a mythical, mathematical universe of space-time fabric and the smooth dance of gravitational fields. And where was electricity and magnetism in all of this? Well, it was sort of banished from the cosmological stage with a vague promise that it might be unified later on. And so the earthly sphere became one of sparks and magnetism and vacuum tubes, and Edison and Tesla and the electric and the electronic ages swept over us. But in cosmology, the mathematical perfection of gravity held sway. The heavenly sphere was one of pristine space-time fabric and singularities, and infinitely perfect physical entities that could not be experienced here on Earth. Sounds familiar. Now, it's ironic that it's said that Einstein kept a portrait of Michael Faraday in his study. It's ironic because Einstein's great achievement effectively removed electricity and magnetism from our exploration of the cosmos. And while we waited for the square peg of electromagnetism to be fit into the round hole of Einstein's theories, over the next 100 or so years, there was a new, complex, sophisticated mechanism developed and constructed to explain the workings of the cosmos. And this is, of course, the Lambda cold dark matter model, what's pretty much known as the standard model of cosmology. So let's have a look at the Lambda cold dark matter model to orient ourselves a little bit. Well, if you look it up in Wikipedia, it's a parameterization of Big Bang cosmology. It's a cosmological constant, lambda, that's associated with dark energy. Dark energy and dark matter, between the two, comprise something like 96% of the matter and energy content of the universe. That other 4%, that thin slice of the cosmological pie chart, as I like to say, is what we can observe and actually directly experience. So here we are, again, in a cosmological model where most of its material content is outside of our experience. It cannot be experienced here on Earth. And I feel like we've taken to a certain extent a step backwards. In fact, dark energy is even sometimes referred to as quintessence. You might remember quintessence of the crystalline spheres in the Ptolemaic model. And I'm amazed not so much by how humans repeat history, but the level of detail that they do so. It's not just a repeat of the same sort of philosophical concept of the separation between the physical nature of heaven and earth, actually reusing specific words again to fill in gaps in our understanding. Now, it took over 1,500 years and the full force of the Age of Enlightenment to shatter those crystalline spheres. But here we are again. From the Age of Enlightenment to what I can only term the Age of Endarkenment. Dark energy, dark matter, black holes. Okay, well, let's focus in on one of them. Let's look at dark matter. Why dark matter? Well, dark matter, the need for dark matter, arose in the late 60s and the early 70s from the work of Vera Rubin, who plotted rotational curves like this. Curve A is the curve that we expected to see, and curve B is what was actually observed. It implied that most of the there was more mass density in the galaxy than we could actually observe. And Vera Rubin reckoned that there was something like about 6 times the dark mass in the galaxy than we could actually see. And very shortly after, it became quite common knowledge, and it became commonly accepted that dark matter constituted most of the galaxy's mass. Now, it's interesting because this whole thing is based on a fundamental assumption that gravity is the only force at work. The equation, the orbital velocity equation, only uses gravitation as one of its parameters. So what if, though? What if we don't know what we don't know? What if there's something missing in that mathematical modeling? What if electricity and magnetism actually could play a role? What if this sort of line of reasoning was applied in a different field of science? Now, I come from a biological background, as you heard, and I remember in ecology class learning about the Lotka-Volterra equation. Now, the Lotka-Volterra equation is a system of differential equations used to model the population dynamics of predator-prey pairs in ecosystems. It was famously used to model the population dynamics of lynx in Arctic hare in northern Canada. Now, what if Lotka found, when he went out and measured the actual population dynamics of lynx and hare, that it didn't really agree with what his model showed? What if he had absolute certainty that his mathematical model was complete? Well, then what if he then, some more what if questions, what if he then proposed that there was a hypothetical creature in the ecosystem that we can't see and left no impact on the environment? In fact, its presence could only be detected through its influence on the population dynamics of the lynx in the air. And what if he did a lot of supercomputer modeling to show that other predator-prey pairings in the world could actually be modeled and predicted if he just adjusted the placement and the relative density of this hypothetical creature that we can't see? Well, it didn't actually play out that way because biologists have a very healthy respect for the incompleteness of their mathematical models. But you see the logical flaw here. Well, what if the similar sort of logical flaw has taken us to incorrect conclusions about dark matter? Well, then we would expect to see discrepancies between what the cold dark matter model predicts and what we observe. And that happens to be the case. And there are actually a list of issues. There's the dwarf galaxy problem. There's the cuspy halo or core cusp problem. There's this issue with the ratio of regular matter to dark matter in some cases. There's a dwarf galaxy pancake problem, which is actually fairly serious. And we have a problem with, we don't have any local dark matter. So we'll go through each of these in turn. Now, the dwarf galaxy problem is also referred to as the missing satellite problem. Now, this stems from computer simulations of the cold dark matter model, which predicts orders of magnitude more satellite dwarf galaxies than are actually observed. So, for example, there are about 11 satellite dwarf galaxies around the Milky Way. But computer simulations, in one case, for example, predicts more than 500. So we're orders of magnitude away from what we actually observe. And then we have the cuspy halo problem. And this refers to, again, computer simulations that predict the density distribution of dark matter in a galaxy. The mathematical computer simulations indicate that it's cuspy. And by cuspy, I mean the dark matter distribution increases sharply to a peak at the center of the galaxy. Well, when the usual mathematical derivations are done based on gravitational dynamics, the inferred dark matter distribution in galaxies is seen to be quite smooth. Maybe there's a bit of a core, hence the core and the core cusp problem, but it's actually a smooth profile. There are no cusps. There's no cuspy dark halos. This is also known as a small-scale cosmology crisis. Then there's the problem with the ratio of regular matter to dark matter. Recent studies of a galaxy-sized cloud of gas, it's actually plasma, Virgo HI 21, this is actually the bullet cluster, but in Virgo HI 21, that the derived amount of dark matter is about 100 times the amount of matter that we can observe. And that's 10 times higher than it really should be. So this is a real disconnect between what the model predicts and what we observe. And now we have this pancake problem. Well, this is observations in January of 2013. Observers from Canada and France at the Keck Observatory were amazed to find that satellite galaxies were moving in unison around the Andromeda galaxy, and they were in sort of a disk-like structure. The similar disk-like structure was found around the Milky Way, which indicated that it's not unique to the Andromeda galaxy, and we'll probably find more of them if we go looking. Now, it's important to note that in the decades of cold dark matter modeling, satellite galaxies are always predicted to be oriented randomly around the larger galaxy. So this is clearly inconsistent with the predictions of the cold dark matter model. And actually, it puts me in mind a little bit of the observations of the phases of Venus by Galileo. These observations were clearly inconsistent with the predictions of the geocentric model. And in a very similar way, the observations of this disk-like structure of satellite galaxies is completely inconsistent with the cold dark matter model, and yet the model persists. And finally, we have the problem with no local dark matter. Now, this story, actually is a story, it's a bit of a tale, starts in 2012 with a report from a group of observers at ESO's Lycia Observatory, headed by Christian Modi Badin. They mapped over 400 stars up to 13,000 light years away from the sun, and used this data to calculate the mass of matter in that volume of space. It was 4 times the volume of space than had ever been considered before. And the intent was to compare the amount of observable matter versus the amount of matter that is derived gravitationally through mathematical means, and compare the two, and the discrepancy, like we saw with Vera Rubin, discrepancy would indicate the amount of dark matter that's present. And what they found when they compared the two was that there was no need to invoke a dark matter component. So there was no dark matter. Well, this prompted an article in the New Scientist where they declared a dark matter conundrum. Well, about a month or so later, there's a paper from another group, headed by Bovey and Tremaine, who took exception to one of the assumptions in this previous paper. And it was an assumption that the rotational velocity of the stars in that region of space were constant as you moved away from the center of the galaxy. So they corrected for that, and they also introduced their own assumptions about the mass distribution in that volume of space. And what they found was actually no, there was the amount of dark matter the model predicted. In fact, just a little bit more, just to be on the safe side. So that elicited another article in the New Scientist where they claimed that the crisis was averted. And there's a really interesting quote in this New Scientist paper that I like where they say, the true believers of dark matter were never really worried. So I find it interesting, the use of the term true believers. And so the story ended for the new scientist. But if you follow that kind of literature and you track these issues, in 2014, Modi Bedin et al. Published another paper finding that the mass distribution assumptions of Bovie and Tremaine actually were completely inconsistent with observational data. And that when they corrected for a mass distribution that was consistent with observational data and corrected for their own assumption about the rotational velocity of the stars, that in fact, again, they found there was a negligible amount of dark matter. There really was no need for dark matter. So crisis averted? No, not really. But there were no headlines. There was no follow-on story in The New Scientist. From the point of view of The New Scientist, crisis averted, the world was safe for dark matter. But why crisis? I'm interested in the use of this word crisis. I happen to live in the UK, and next week we're going to vote to see if we stay in the EU or not. Now, proponents of both sides present various crises that will ensue if we go one way or the other. If we leave the EU, the national health system will suffer, the real estate in London will go down, and foreign exchange, the UK pound will suffer. Or if we stick with the UK, we'll lose sovereignty, we'll lose control of our destiny. So crises on both sides. But why crisis with dark matter? I don't understand that. We find that there's no such thing as dark matter. It's not going to change the real estate prices in London, so I don't understand what the crisis is. Well, it's a crisis in belief. And when you have belief systems in science, you've got trouble. And belief systems come wrapped in certainty. And when you have certainty, our rational mind ceases to play a primary function in our cognitive processes. But really, I can't say it better than Mark Twain. It's not what you don't know that gets you into trouble. It's what you know for sure that just ain't so. And so we have a problem with certainty. And when it comes to certainty, I really can't recommend a better book than this book by Robert A. Burton, On Being Certain or Believing You're Right Even When You're Not. And in it, he covers a range of material about certainty and our sense of knowing. He presents a very interesting example called the Challenger study. This pertains to how we remember things around dramatic events in our lives. And when the space shuttle exploded, Dr. Ulrich Neisser, a psychologist and the father of cognitive psychology, had 106 of his students record in their journals what they were doing at the time, what was happening, how they felt, all of the details they could remember when the event actually happened. And then he interviewed them 2.5 years later. Now, as you might expect, about 25% of them got a lot of the details completely wrong, and at least half had a few of the details incorrect. But what was really interesting was the reaction of some of their students to their handwritten notes. In the words of one of the students, "That's my handwriting, but that's not what happened." So the students had complete certainty over their sense of knowing, even in the face of very convincing evidence, their own handwritten notes. Now, Burton uses another example along these lines, and it has to do with Cotard's syndrome. And this is Dr. Cotard, who described a syndrome in patients who develop a delusion of negation, a negation of their own existence, negation of limbs, that their limbs are putrefying. And what's really interesting about the syndrome is the unshakable belief in these patients that they're dead. Now, Burton describes one case, Miss B, who came into the hospital with a very severe case of viral encephalitis. And while she was there, she began to complain about things not feeling real and that she was dead. The hospital staff had her hold her hand to her heart so she can feel her beating heart, and she admitted she could feel her beating heart. But she argued that the beating of her heart was in no way evidence that she was alive because she was clearly dead. She was absolutely certain she was dead, all evidence to the contrary. So Burton uses Cotard's syndrome, the Challenger study, placebo effects, to show that when there's a conflict between rational evidence and what we see with our own eyes versus our feeling of knowing, our sense of rightness and correctness, that feeling wins out almost every time. And he argues that there's some physiological basis to this feeling of knowing that is so powerful that it makes our rational thoughts feel wrong or irrelevant. And he argued that it had to do with the limbic system. Now, the limbic system is associated with our primitive brain. It's the seat of strong emotions, fear and hatred and anger. In fact, the amygdala controls all those strong emotions. The hippocampus plays a role in converting short-term memories into long-term memories. Now, Burton describes a cortical mapping study where they stimulated regions of the temporal lobe associated with parts of the limbic system. And he described patient responses where if that particular part of the temporal lobe associated with the limbic system was stimulated, they had a feeling of certainty. They had a feeling of certainty, a sense of knowing, a déjà vu, a sense of familiarity in a strange environment. So he argued that if it's possible to stimulate the brain and produce these primary feelings of knowing, it's very much like other primary feelings like anger. And he argued that our feeling of certainty is actually closely associated with these primary feelings in the limbic system. And it's not surprising that certainty is connected with the limbic system. Recent neurological research has shown that social threats and rewards evoke the same neurochemical responses as actual physical threats and rewards. A threat to our certainty evokes the same neurotransmitter response as an actual physical threat. So it would seem to be connected to the limbic system. So we have a number of issues, things that we're up against. Well, we don't know what we don't know, but we always seem to forget that. We have certainty in what we think we know, and this limits the acquisition of new knowledge. There's this myth of the rational, objective mind when we're really under the control of our limbic system. And what we really need to do is encourage the pursuit of uncertainty, but that's completely counter to our physiology and our evolution. So here we are, with all of our beliefs and our biases and our blind spots, trying to make shapes out of the darkness. And we construct stories that match the shapes that we think we see. So should we stop trying to discover what's out there looking back in the darkness? I don't think we could, even if we tried. We're compelled to ask these basic questions like the clever king about the cosmos, the sun, the earth, the stars, and life itself. But we're also compelled to construct stories to help fill the gaps in our understanding, to give us satisfying answers, however wrong they are, to answer those basic questions. So like any device that we use to investigate the cosmos, we need to understand the limitations of our own mind. When the instrument is giving us noisy or valid data, are we believing what we see or seeing what we believe? I would argue that dark matter is more of a manifestation of gray matter, so we end up seeing it everywhere we look. It's been shown that our rational mind cannot work independently of our threat-reward responses. We're under the sway of the limbic system like some great psychological schoolyard bully in our mind. Our ability to objectively observe is severely limited by our biases and beliefs. We know that. And yet we have this myth of the rational, objective mind. We think we've got it all figured out. Just a few more pieces, we're almost there. But how can we when we don't know what we don't know? Have we learned nothing from the clever king? Which reminds me, I haven't actually finished the story of the clever king and the sage. The sage learned that it was unwise to provoke a frustrated and angry king. And he spent a few years learning even more wisdom in the king's dungeons, unfortunately. The king learned wisdom over many years because he discovered that he could never complete his great machine and that it was probably based on faulty principles anyway. And so he learned that the sage was actually right. So he released the sage, who was very ancient by that time, and they, together, in the remaining years, taught the clever people in their kingdom about the foolishness of certainty and the rich rewards of uncertainty. Now, having said all that, I have a few qualified certainties of my own. I'm only human after all, and I'm encumbered with my own belief systems. So I believe that there is no matter and energy in the universe that cannot be experienced and experimented with here. We do not live in an island of normal matter in an otherwise exotic universe. The darkness beyond the campfire is not inherently different, it's just as yet unlit. That the universe is a manifestation of gravity and electricity and magnetism in a glorious interplay that we're only just now on the verge of glimpsing. And that in this quest, we need to embrace uncertainty and allow ourselves only a qualified, provisional understanding of what we think we see in the darkness beyond the campfire. Thank you.